the roofers are on my roof right now. They're replacing our roof from hail damage. So if it gets too loud, I apologize now in advance for that. Okay, so as we know, the type of radiation that we're dealing with in dental radiography is ionizing radiation. And this is why it is so important for us to understand this process and understand that this little tube that we're firing at people is putting radiation into their body, which can cause biological damage. So we don't want to just keep retaking for the perfect image. We want to try to practice a LARA and keep it as low as reasonably achievable at all times. So the radiation, like we said, is ionizing. It can create ions by removing that electron. Then we can have particulate radiation, which is tiny particles of matter that do possess mass. They travel in straight lines at high speeds. There are 4 different types. We're not going to talk too much about that. So you don't need to really know much about particulate radiation other than the fact that it does exist, okay? The 4 different types are beta, cathode rays, alpha, protons, and neutrons. I will not ask you that, but you'll just want to know that particulate radiation is a type of ionizing radiation. Electromagnetic radiation, you do want to know, because that's where our ionizing X-rays come in. That's where they fit. They are a propagation of wave-like energy. They have no mass, and they can travel through space or matter. When they're created, they have an electromagnetic field that is positioned at right angles to each other. You don't need to know that either. Just know that they create this electromagnetic field. As I'm going through this, if you guys kind of want to highlight things that I say are important, that can be helpful too. Electromagnetic radiation can be man-made or naturally occurring. And some of those electromagnetic radiation that fall in that chart that we showed you in your book can be ionizing or non-ionizing. Not all of those radiations on that chart are ionizing, but X-rays are. And that chart is on page, let's see. Page 11 of your textbook. Okay, so on that spectrum, they're arranged in order of energy level. So the ones that are the lazy, low wavelength, non-ionizing are at the top. And as we come down, we can see the X-rays fall down. X-ray and gamma rays are the really high frequency, short wavelength energies at the bottom. In the particulate concept, they call them discrete bundles of energy called photons or quanta. And the wave concept is what I want you guys to really focus on for us. And that is the velocity, which we talked about is the speed of the wave. The wavelength is the distance between the crest of one wave to the next. And there's a really good video that gives you this visual. It draws it all out for you, and I think that it'll make it really clear to you. Frequency is the number of wavelengths that pass a given point at a certain amount of time. A mnemonic that I was given when I was in radiology tech school was SHAL, and what that means is short wavelength, high energy, and long wavelength, low frequency, low energy. So I would always write that at the top of my test so that I would remember short wavelength, high frequency, high energy, long wavelength, low frequency, low energy. Now I've listed, and I'm not going to read through all of these to you, but X radiation on page 12, there's a box that talks about the properties of X-rays. I will talk about some of the ones that I think are the most important for you to remember. X radiation is high energy. It is ionizing electromagnetic radiation. They are weightless bundles of energy. They carry no electrical charge. They travel in waves with short wavelengths, high frequencies at the speed of light. So all X-rays are traveling at the same speed. Not all X-rays have the same energy. When an X-ray leaves the tube, they call it, I believe, polychromatic or polyenergetic. They have, all of them have different energies, and that's why when those X-rays come into the body and interact with matter, they have differing effects. Some of them that have high energy will go directly to an inner shell electron, be completely absorbed. Some of them will travel without interaction. Some of them will hit a lower energy orbiting electron and bump it out and then create another Compton scatter or X-ray photon. So there's all different things that can happen. They do travel in straight lines. However, X-rays diverge. They want to spread out. And I do believe there was a picture of a flashlight. So I always use that analogy. Can you hear the hammering? So a flashlight, when you shine a flashlight on the wall, the light diverges and goes out. And that's exactly what X-rays do. So when we pull our flashlight back, which is what we do when we use a longer PID, we're using more of that focused center, penetrable part of the beam. If you take a flashlight and you move closer to the wall, it diverges really far. So that's kind of how I think about how X-rays function. Tell me, do you guys all feel okay about the components of the X-ray tube? The extension arm, the control panel, the metal housing, and what all of those things do? Or would you like me to review that?
Can we review it?
I'm sorry, say that again. I have one person that says I understand that part, and then Dana, I couldn't hear you. I couldn't understand what you said. I could see that you were speaking.
For me, I think that I understand it, but I know that there was like a couple questions on the quiz that I just questioned myself if I was getting it right or not. So since we haven't gotten over that yet, like I'm not really 100%. You know what I mean?
Okay. I will just zip through these quickly and give the brief overview of what they are. Control panel obviously is all of our exposure buttons, our KVP, our MA, our on-off switch, time. Extension arm just is what the arm that suspends our tube head and enables us to position it. That metal housing, that outer housing, surrounds the X-ray tube transformers. It's filled with oil, and the purpose of it is to absorb X-rays and heat. So, because like I said, those X-rays want to travel in straight lines and they want to diverge. So the metal housing and all of that is an attempt to keep everything contained. And that's why it's so important if you would have an X-ray tube head that was leaking oil or having a problem, you definitely want to get that checked out because that could be a problem. Again, the oil is there to absorb heat. The tube head seal can be aluminum or lead glass covering of the tube head, which permits the exit of X-rays. It seals in the oil and acts as a filter to the X-ray beam. So all of that, that glass window and that seal and aluminum filtration is all found at that tube head seal. The X-ray tube is what we've talked about with the cathode anode in that glass envelope. That is the heart of X-ray production. Then we've got the transformers, which we discussed the step up and step down. Like I said, the aluminum discs are for filtration of long, lazy wavelengths. Lead collimator, the purpose of the lead collimator, remember lead is not going to allow anything through it. So it is to restrict the size of the beam. We're not going to use lead for filtration because lead will filter it all out. So lead is going to restrict the size of the beam to make sure that we are only using enough radiation to cover the area of tissue that we're interested in. That way we're not firing radiation all over our patients. And then the PID, or the position indicating device, and remember I said sometimes they'll call it beam indicating device, a BID, is that lead lined cylinder that aims and shapes the X-ray beam. And you'll often hear people refer to this as a cone because back in the day it was cone shaped, which I think one of the questions maybe talked about the cone. You would never want to work anywhere that's using a cone because that's just firing X-rays everywhere. Okay, so those are the components of the X-ray machine. Then I tried to simplify all the components of the tube. The lead glass housing is that glass housing that contains, it's a vacuum. First of all, it's completely airtight. It does have a little window that will allow those X-rays to leave that glass housing once they've been created. The cathode is the negative side, has the negative electrode. It has that tungsten wire filament that is where the electrons are created through thermionic emission. Okay, I actually have a whiteboard here that I'm going to try to use. So this is the cathode on the negative side. And then I'm gonna, I don't know, can you guys see that?
Lift it up just a little bit. Much better.
Yeah, I can see it.
Okay, so we've got cathode and anode. All right, so electrons will build up around the negative cathode like this. And then when enough of those build up through thermionic emission, they will be with the high voltage circuit. We will apply kVp between 65,000 to probably more like around 70,000 in our dental units. Will provide enough energy to give them the speed or penetrability to drive across to this anode target right here. Okay, at that anode target is where they become X-ray photons. And they will then come off of the anode target like such. Okay, so the purpose of the anode target is to create X-ray photons. The smaller the target, the more focused and what do I want to say? We like a narrow beam. Remember I told you they want to diverge a lot. So there is a focusing cup that as those electrons are driving across to that anode, it's kind of like the preschool teacher keeping all the kindergartners or the little preschoolers together in a row. That cup keeps those from diverging from the cathode filament over to the anode. Once they get to the anode, the smaller the target, the better the image, the sharper the image those X-rays are going to be able to create for us because they're more focused. Otherwise, they'd be all willy-nilly flying all over the place. They'd come out and you would have all kinds of unsharp edges of your image. So small focal spot is very important. We're going to talk about that later. But remember, the cathode is negative. That's where the electrons are formed through thermionic emission. They create this electron cloud around that filament, and then they are given the energy through the high voltage circuit, or KVP, to be released over to the anode target, which is the source of X-ray photon production. And remember, anytime they're talking about target, that's what we're talking about. When we start talking about distances and they say target to surface, that's the anode target to my skin, to my cheek. When they say target to object, that's to the tooth that I'm imaging. And then they will also say target to IR, or image receptor, which is self-explanatory. So that's the component of the components of the X-ray that I want you to know and really understand how that's working inside the tube. The electricity is just the energy that is required for us to make X-rays. We have to have a source of energy. So the X-ray unit is plugged into the wall, and we're either plugged into 110 or 220 from the wall. From the wall, we're getting AC current, which is alternating, is what AC stands for. So that means that they'll travel in one direction, and then there's a slight hesitation and the electrons will travel in another direction through that conductor. When we're trying to produce an X-ray, we want a constant steady flow, because any hesitation can affect what our image looks like. So we have a rectifier in the unit that takes that AC current and changes it to direct flow current. So it's flowing in one direction all the time, so we don't have those hesitations, and we get a nice steady flow of electrons to give us a really sharp image. The amperage is the measurement that we use for the number of electrons that we're going to produce. Amperage will control how many electrons move through that conductor. You may also hear that called current. So anytime you hear milliamps, amperage, current, number of electrons, quantity, all of those are referring to MA, or amperage. Voltage, on the other hand, is a measurement of that electrical force that we're giving those electrons that they need when it's time to go from the cathode, which is negative, to that positive anode target. It's measured in kilovolts in our units. So anytime you hear KVP, KV, we're talking about the quality of those electrons. How penetrable are they? How fast are they traveling? So just remember that quality is KVP, quantity is amperage. The circuits are the filament circuit, which is that itty bitty wire. And remember that I told you that itty bitty wire needs not a lot of heat, or I should say electricity applied to it, because it could bust that filament, but it needs enough heat to drive those electrons off of that filament to produce our electron cloud, so that we have enough electrons to create X-rays. The high voltage circuit is controlled by KVP, and that's going to give those electrons that driving force that they need to travel across to the anode target. We have transformers that either step up that electric supply from the wall, or step it down. So the step down is going to decrease the voltage from that incoming 110 or 220 to 3 to 5 volts approximately. Some are different, but that's what the filament circuit requires. That step-up transformer is going to increase the voltage up to 65,000 to 100,000 for the high voltage circuit. And then there's an auto transformer sometimes as well that just kind of keeps things constant, because remember I said we don't want any fluctuation or hesitation. So that auto transformer is in there to kind of keep things leveled off. Okay. What I did here is just kind of summarize the production of X-rays. So electricity supplies the energy to the X-ray machine from the wall at 110 or 220. The current is then directed to that filament circuit, which is our low voltage, and we use that step-down transformer to convert those 110 or 220 volts down to 3 to 5 to create enough energy at that filament to create our electron cloud around that wire. Those electrons are then released by thermionic emission from the filament wire when that high voltage circuit is activated. When is that activated? That's activated when we push that exposure button. When we push that exposure button, that high voltage circuit is activated, and those electrons that were produced at the cathode are now going to be accelerated across the X-ray tube to that anode target. They travel from cathode to anode, they strike that target, and their energy now becomes X-rays and heat. And we know that only less than 1% of all of that energy actually becomes X-rays, and the rest becomes heat. Now, what I don't, in some of the discussion questions, of all of the energy that's created by the electrons, only 1% of what happens at that anode target becomes X-rays. But when those X-rays come out of the tube, it's hard to say for sure what percentage of those X-rays actually strike the patient, interact with the patient, etc. So the 1% comes in, not that the patient is only going to receive 1%, but that of all of the working that's going on inside of that glass envelope, all the X-rays that are produced at that anode target, a lot of that energy is given off as heat and absorbed by the oil and the housing and all of that, and only 1% of all of that energy inside of the tube will become X-rays. Does that make sense? I had some people that were stating that the patient was only receiving 1% of all of the X-rays that come out of the tube, and that's not true. They're going to absorb more than that, but the 1% comes in when we're talking about production. I just wanted to make sure that we understood that. Okay, so then the heat is absorbed by the insulating oil inside of the tube head. Those X-rays are emitted in all directions inside of that glass housing, and only a small number of those will exit through the unleaded glass window. The X-rays travel through the window, the tube seal, those aluminum discs that are going to filter out the long wavelength, low frequency, and then the beam is restricted by the lead collimator. And then the primary beam, the most penetrable center part of that X-ray beam, is going to travel down the lead-lined PID and exit the opening of the PID at your patient. So that is basically a recap of that whole scenario. Is everybody clear on that? Does that help kind of clarify how that all happens inside the tube, when it leaves the tube, and what comes out of the PID?
Yeah, a lot.
Okay. Then we're going to talk about the different types of X-rays that can be produced. We have general radiation, which is what we're going to work with mostly. Sometimes it's called breaking or bremsstrahlung. And the reason it's called that is because when I was talking and I was showing you this little picture, these X-rays are going to come really quickly, and they're going to slam into that target and abruptly stop. So that is why they call it breaking or bremsstrahlung. So it's high-speed electrons that are suddenly stopped at that anode target. They consist of X-rays of many different energies. Like I said, they can have lots of different energies and wavelengths. 70% of the X-rays produced are produced in this manner. So this is the biggest percentage of the X-rays that are produced. Characteristic radiation is another type of an X-ray, of X-rays that can be produced. A high-speed electron will dislodge an inner shell electron from that tungsten atom and causes ionization of that atom. Once the electron is dislodged, those remaining electrons, so you've got an electron that's been dislodged in an inner shell, let me see, and then what happens is kind of like a cascading effect where one electron has been bumped out and the others will kind of come down to fill its space. So I don't know if I can draw this very good for you guys. So this is horrible, but basically if I had an electron in one of these outer shells, and or we'll say the second shell, the L shell, and one's gone, like you can see there's an open space there. So the next shell bigger, the outer shells, it's almost, I'm trying to think what something, it's almost like the domino effect. Like an electron will cascade down into that spot, which will make the next shell cascade one down into the shell below its spot. Does that make sense? So that's what's happening during characteristic radiation. That high-speed electron will bump out an inner shell electron, causing ionization. Once that electron's bumped, the remaining orbiting electrons will cascade down to fill those vacancies. This will only occur if we are using 70 kVp or higher. The binding energy of an inner shell, that most inner shell electron, is about 69 keV. So we need to be using at least 70 to bump one of those out. This accounts for a very small part of X-rays in a dental machine. So we don't use this very much. I want to say it makes up only, I don't even know, very, very small percentage. Okay, so primary radiation is the penetrating X-ray beam that exits the PID. That is the primary beam. And of all things, as a dental radiographer that you want to avoid, that is it. So no more holding X-rays, no more holding tube heads, no more putting your body in the line of fire. Secondary radiation is the X radiation that is produced after that primary beam interacts with matter. So that is where our scatter comes in. And in fact, the next definition that I have on my sheet is scatter. So it's a form of secondary radiation that results from that X-ray beam being deflected from its path with its interaction with matter. So if an X-ray comes in and it gives up some of its energy, and then the rest of its energy goes in another direction, be that Compton or coherent scattering, that is what is detrimental to both the patient as well as us. So that's the reason for the lead shielding, the proper thickness of the walls that we stand behind, the lead in our windows in the X-ray rooms. You want to make sure that you are positioned at a good distance, which is about 6 feet from your patient, at a 90 to 135 degree angle from that primary beam. So all of those things are important for that. All right, interactions with radiation. I found a YouTube on that as well, which talks about these interactions that I felt like really help clarify it. So those are out there too. Like I said, we can either have no interaction. If we have no interaction and the X-ray photon comes into the atom, goes right through and doesn't hit anything at all, doesn't dislodge an electron or anything, it goes straight to the image receptor, that is going to create the density on the film, the blackness on the film. So it's important that we, and obviously we have a lot of that, probably most of it is scatter, but there's a big part of it that goes through and doesn't interact at all, because if you look at an image, look at all the blackness on a dental x-ray, all of that was created by no interaction. So that is important to help create our image. The absorption of energy is also called the photoelectric effect. And what happens there is that X-ray photon is completely absorbed by the patient's tissues or matter. So if you think about like an amalgam, it completely absorbs it. It doesn't allow any X-ray to travel through it. So it's going to appear completely white because it has not interacted with that image receptor at all. So the silver halide crystals that are on film or the little pixels that are on a digital haven't been excited or anything by that X-ray, so they're just going to be completely white. The photoelectric effect makes up about 30% of the interactions of the dental X-ray beam with matter. And then, like I said, Compton scatter makes up about 62% of our interactions. And we've talked about what that is, where the X-ray photon comes in, gives that part of its energy to an outer shell electron, and then it leaves behind a Compton electron or Compton X-ray photon that travels in another direction, causing your body to absorb that. So we don't want our patients to have that, or us. So Compton scatter is the most detrimental. Coherent scatter is another type of scatter that can occur, does not account for much in dentistry, about 8% of our scatter. The X-ray photon is a low energy photon. It interacts with an outer shell electron. It really has, it does not change the atom at all. It just takes off in another direction and creates scatter in that way. So there's no loss of energy and there's no ionization with this. It's just creating scatter. Okay, that is chapter 2. How do we have any questions so far with that chapter? I don't see any questions, so I'm going to continue to chapter 3. I think chapter 3 was where many of us got a little overwhelmed. So we will hopefully be able to clarify, slow this down a little bit, and maybe I can help you guys wrap your brain around some of this, because I know this is kind of heavy stuff. Basically, chapter 3 talks about radiation characteristics. So the characteristics of radiation are basically how much are we producing and what quality is it. So quality is controlled by kVp. And this is what I always did to keep it all separate. I would make myself a little chart like this, and I wrote quality and I wrote quantity. So we'll talk about quality first. Quality is controlled only by kVp. It's going to give us the energy or penetrability of that beam. Sometimes they'll refer to it as speed of those electrons. So high kVp is going to equal high energy. And the reverse is also true. Low energy kVp will create low energy beam. Okay. The current units that we work with are, you can set them to 60 kVp or 70 kVp. As you know, hopefully you remember that KVP is the controlling factor for contrast. So I would always put that under quality as well. Contrast. There is no other exposure control that you would ever adjust if you wanted to change contrast. KVP is the only thing that affects contrast. And it is important to remember that it has an inverse relationship with contrast. So if I increase KVP, I am decreasing contrast. And if I decrease contrast, I'm going to have a lot of gray because low contrast, long scale, lots of grays, okay? Then the opposite is true. If I decrease KVP, I'm going to increase contrast, which is black and white. And if you remember, we talked about, okay, so here's what I have so far. Black and white is going to be important for a general dentist that is wanting to detect decay. And we might like a little bit higher KVP with some more grays if we were looking for periodontal disease. They like to see a little bit more detail that way. So that's quality. Let's talk about KVP and density. KVP does have a slight effect on density. So just think about if I'm applying more KVP, those electrons are going to be more penetrable. They're going to have more energy. So chances are real good that more of those electrons are going to make it across, become X-ray photons and exit the tube. So it does have a slight effect, and it has a direct effect with density. So if I increase KVP, I'm going to have a slight increase of my X-ray photon production. But it is not the controlling factor. If I want to increase density, it's a much more efficient idea to utilize my MA or my time to do so, not KVP. Because if you start messing with KVP, now you're messing with your contrast too. So it's messing with two things where MA is only going to change density and time is only going to change density, because remember, there is nothing else that we can touch to control contrast other than KVP. So do understand that it does have a slight increase on density, but it is not the controlling factor. KVP and exposure time have an inverse relationship, because if I increase time and I want to keep my image the same, let's say I took an image and now I'm going to increase my time, but I want the image to come out the same. I want it to be the same density, same contrast, everything. I am going to have to decrease my KVP in order to maintain that same exposure. Because if I'm firing longer, it's going to increase everything. So I've got to kind of balance things out. And we're going to talk about that with our mass problems that we touched on just a little bit. So when we get to MA, we'll talk a little bit more about that. So just remember, the main thing about KVP that I want you to remember, because I know this is probably all somewhat confusing. Remember KVP and contrast. That is the most important relationship. It is an inverse relationship. If I increase KVP, I'm decreasing contrast. If I decrease KVP, I'm increasing contrast. Understand what increasing and decreasing contrast means. If I have high contrast, I have black and white, not a lot of gray. If I have low contrast, I have a long scale, lots of grays. So just remember that about KVP. Now, For quantity, that is going to be the number of electrons we produce, the number of X-rays that actually are created from those electrons. So now we're talking quantity. Quantity is number of electrons or X-rays produced. Now, the quantity can be affected by, it can be affected by MA, time, distance, and somewhat kVp, okay? So I would make my little chart like this, and I would list everything that has an effect on quantity. So it's the controlling factor of quantity is MA and time, not kVp, remember. And this one's easy because it's a direct effect. If I increase time, I increase quantity. If I increase MA, I increase quantity. If I decrease time, I decrease quantity. And if I decrease MA, I decrease quantity. So those are all direct relationships. So that is for MA and time. Now, when we talk about distance, think about if you, again, let's use the flashlight and I'm shining it at the wall. If I stand at 3 feet from the wall, the beam of that flashlight is brighter than if I move back at 6 feet. It becomes less powerful. So the same thing happens with our X-ray tube, or if I'm the radiographer and I'm positioning my body 3 feet from that source or that anode target versus 6 feet from that source or anode target, I am getting less when I move farther. So the distance is an inverse relationship to quantity. So if I increase my distance from the source of radiation, then I am decreasing my exposure. Does that make sense? So okay, so distance is different. MA and time are both increase one, it's going to increase your quantity. Increase time, increase quantity. If I increase my distance, I'm decreasing the quantity of X-ray that's able to reach me. If I move closer, or let's say I'm using only an 8-inch PID versus a 16-inch PID, the 8-inch PID, if I'm using all of the same exposure factors, are going to supply more. It's going to be more powerful, right, at my, because I don't have that extra 8 inches of lead filtration and all of the stuff that it goes through before it gets to me. So plus it kind of diverges out and it decreases anyway. So distance is opposite. It is an inverse relationship with the quantity that is produced or received by the patient or the radiographer that may be standing too close to that source of radiation. So that's quantity. So quality, kVp, quantity, MA, time, and distance, and a little bit kVp, but that's not the controlling factor. So when we talk about beam intensity now, basically beam intensity is the compilation of all of that. It's the product of the quantity, how many electrons do I have, how fast are they traveling, all of those things. So KVP, MA, and time can all affect my overall beam intensity, and distance can too. So all of those things are important to remember when we're talking about beam intensity. The distance from the source of radiation, okay, if we increase it like I stated, it's going to decrease that overall beam intensity. The different distances that I want you to understand and be able to, if you saw it in a question, be able to understand what we're asking for is the target to surface distance, which when I say target to surface, if you look at page 28 in your book, figure 3.7, it shows you that that target to surface distance is to my cheek, to my skin. And then there's a target to object. Whenever we're talking about the object, that is what we're actually imaging. So it's the tooth in this case. And then the target to receptor is from that anode target to the image receptor, be it a sensor, a piece of film, or a PSP plate. So those are the distances that you may hear mentioned. Now, the inverse square law, everybody despises the inverse square law and freaks out when they see this and they see the problems. The inverse square law is basically just a law that was written that basically is stating what I'm telling you. It's just giving specific numbers to that whole distance relationship with the source of radiation. So what this square law says is that the intensity of radiation is inversely, I was telling you distance has an inverse relationship, it is inversely proportional to the square of the distance from the source of radiation. So if I take my original intensity and I put that over X, because we're usually trying to find our new intensity, you take the new distance, which would be distance 2 squared, over your original distance squared, and you work out the math. It basically, in a nutshell, if you're doubling your distance, you're going to either, if you're doubling your distance, you're going to cut your radiation exposure by a quarter or a fourth. And if I'm moving closer, if I'm at 6 feet and I'm moving into 3 feet, I'm going to multiply by 4 my exposure. So basically that's the inverse square law, is just saying that that distance, that doubling or reduction of distance is going to increase or decrease your exposure. Then they discuss a little bit about the half value layer. The half value layer is that aluminum. That's what they're talking about, is the aluminum that's placed in an X-ray tube in order to reduce the amount of radiation coming through that aluminum by half. So it's whatever thickness of aluminum is necessary to decrease the X-rays by half that are coming through that tube. All right, that's chapter 3, guys. That's the really heavy, confusing, hard stuff. So as far as the inverse square law goes, in your book on page 29, they give an example. It says, if the target to receptor distance is changed from 8 to 6 inches. So I'm going to attempt to show you this. Intensity 1 over intensity 2 equals distance 2 squared over distance 1 squared. Now this is inverse square law. Okay, if you guys can see that. The reason if you look at this formula, it's inverse. When I look at the intensity side, the first intensity is on top, the second intensity is on bottom. And when you look at distance, I am putting the second distance on top of my equation and the first distance on the bottom, and that is very important. The other thing that is very important is that you remember to square the distances, hence the name inverse square law. So if I were going to plug in numbers here, it says that my target receptor distance went from 8 to 16 inches, and they do not give me any intensity. So if nothing is given, I'm going to use 1 for my intensity. So I'll plug numbers in. 1 over x, we're going to call I2x because that's what we're trying to find. And it went from 8 to 16. Okay, so you can see I've plugged those numbers in. I've got 1 because they don't give me an intensity, so I'm just going to use 1. I'm trying to find the new intensity, which is represented with x. The second distance we're going to is 16, and I want the second distance on top. We started at 8. We need to remember to square these, but I'm going to simplify this and reduce this first, because I can reduce that to 1 and 2 over 1, which makes it much easier to work with, because 8 goes into 8 one time and goes into 16 two times. So I brought that over and reduced my fraction. So now I have 1 over x equals 4 over 1, like that. And now I'm going to cross multiply. So this is kind of where I am, if that makes sense to you. I take 4x, equals, I had my 4x here equals 1. So I'm going to divide by 4 on each side, like that. And it's like 0.25 or something, or 1/4. You can call it 1/4, or you could call it 0.25, whatever you want to call it. But that's my new exposure factor. Now, when you're looking at these problems, you can always, before you even start solving the problem, and a lot of these you don't even have to use the formula, because you know if it's doubled, if the distance is doubled, I'm going to decrease by 1/4. And if my distance is moving closer by half, then I can multiply by 4. And I can easily come up with where my intensity is going to fall. So if you know that I'm going from an 8-inch to a 16-inch, I can look at that problem before I even begin to solve it, even if I didn't know the formula, and I could say, okay, if I'm going to a longer PID, I know that my intensity is going to decrease. So let's say you were given a problem on a test, you could mark out any intensity that was listed there that was higher than your original intensity, because you know if you're moving farther, distance, increase, decrease in exposure. Okay? Have I completely confused you guys?
No, I think it's more understandable.
Okay. So
Can I see your whiteboard really
Yeah.
quick so I can finish the notes on it?
yeah,
Thank you.
can you see it?
Yep, I can. Okay. I got everything now. Thank you.
You're welcome. All right, so that's chapter 3. That's the one that most students really struggle with. And I don't want you guys to feel bad at all for that, because you are at a huge disadvantage because we're not in person. I can't interact with you in person, and we could, we would go through these a lot. I would be all over the big board at school. So hopefully this helps. I hope that my little reviews are helping. I try to take these chapters that have all of this stuff and kind of condense it. And then that coupled with like evolve and going on there and maybe answering some of those questions will hopefully help this stuff stick. I also went ahead, I didn't know if you guys wanted me to review chapters 4 and 5 as well, but I've done reviews for those as well. If you would like me to go through that, I'm happy to do that as well. Would you guys like me to?
Yes, please.
Okay. All right. So now we're going to apply what happens when this ionizing radiation comes in. What can that do to our body? It can create, like I said, it can ionize, which bumps out electrons, and then you've got these dislodged negative electrons, and it can also create free radicals, which if any of you buy face creams, they always talk about free radicals and how horrible that is to our tissue. So free radical formation is an unchanged atom or molecule that has a single unpaired electron in its outermost shell. This occurs when that ion comes in and reacts with water, which, as we know, I think like 70 to 80% of our cells are water. So there's a lot of that happening. And it can, when that happens, when a X-ray comes in and reacts with water, it can create these free radicals. It can also create toxins that are almost like hydrogen peroxide formula in the body, which is not good inside the body. So these are the different theories. The direct theory is, these are theories of injury. So the direct theory states that ionizing radiation comes in and hits critical areas within the cell that cause damage to that cell. They rarely occur. Most X-rays that we encounter pass through the cell, causing little or no damage. So most of the time when we have X-rays, it, yes, it does damage biological tissue, especially like dental X-rays are so low that most of those go through without interaction or very little damage, and that damage is able to repair itself, and we never even know it happened. The indirect theory is where those X-ray photons are absorbed by the cell and they form toxins that damage the cell. So they come in and they interact with water, with the water in the cell. When that occurs, free radicals are formed. They can combine to form those toxins that damage the cell. And this occurs quite frequently, like I said, due to all the water in the cells. Now, let me see where our little dose response curves are. A lot of times people get really hung up with these too. On page 33, we've got dose response curves, and it takes me back to, I don't even remember if it was geometry or what, where you're plotting things on a graph. I'm not a mathematician. It's not my thing at all. But if you think of these curves, if something has a threshold, if I say that there is a threshold on something, that means I have to meet a certain amount before I see a result. So on the threshold curve, which is the first one noted here, we've got dose charted on the I believe that's the X, and response on the Y, or on the up side of this chart. So threshold means I would have to be exposed. I know that I have to have at least 25 millirem before I see any effect to my tissue, let's say. So you can see that that curve does not start until where that little arrow is pointing and it says threshold. That would be, let's say, our 25 millirem mark. At that point, as dose increases, my response increases. The more dose I receive, the more response I have. Now, if we look at linear, non-threshold, which are the next two, the linear non-threshold, the dose indicates that a response could be seen at any dose. So we could see result. We could see on some people, maybe it's 25, on some people, maybe it's 50, on some people, very, very little. So that means that we could see a response at any dose. A threshold is the only curve that specifically states to us that I see nothing until I reach 25 millirem. Now, all of a sudden, I see redness and patients exhibiting hair loss or whatever the case may be. That would be my response. So that is how the dose response curves work. You're going to hear them talk about radiation effects as being stochastic or non-stochastic. Stochastic, the word means random in nature. So if it's stochastic, it's just kind of maybe it happens, maybe it doesn't. It's random. I'm different than you. A different amount might affect me. So the probability of a reaction increases with an increased dose, of course, but the severity doesn't necessarily depend on the magnitude of that absorbed dose. The results are random. And some examples of this would be genetic mutations. Sometimes we've seen leukemia and other cancers and tumors that some patients exhibit and some patients don't. Now, the opposite of that is non-stochastic. These are deterministic, and this is the one that I remember all the D's. It is dependent on the dose. It's determinist. It's determined by the dose. So a threshold of exposure must be met and exceeded in order for these patients to show the radiation effects that we're referring to. So redness of the skin, loss of hair, cataracts, decreased fertility. Teratogenesis is anything that could affect a baby, a teratogen, and fetal death. So on the non-stochastic, just remember it's determined by the dose. Stochastic is random. Some people will exhibit, some people won't. There's no threshold. Any amount could cause an effect. So that's the difference between stochastic and non-stochastic. Then we have, let's say once we've been exposed to radiation, we have a sequence of radiation injury. We've got the latent period. We're also going to talk about latent when we discuss film. A latent image on film is, let's say that I've taken an x-ray, but I haven't, and it's on film, but I haven't run it through the processor. That image is there, but I can't see it yet. It's there, but it has to run through the developer and the fixer and the water and be dried before I can see that image. Kind of the same thing with radiation exposure to our body. I'm exposed to it, the damage has occurred, but that latent period is the time between that exposure and when I actually see clinical symptoms of the effects of that radiation. Then once you do, the period of injury is the time that those symptoms or problems are visible or noticed. And then there's the recovery period. So not all injuries are permanent. The damage can be followed by repair. Some cells will go back to their original functioning stage. Some will be repaired at a less than normal. Some die and are never repaired. So this is where it's important to remember that the effects of radiation are additive, cumulative. Any unrepaired damage in those tissues will accumulate. And those cumulative effects can result in cancer, cataracts, or birth defects. So latent period is that time that we don't see. We've been exposed, the damage has been done, but we don't see the effects yet. Injury period is the time that we do see the effects, and then there's a recovery period where the body tries to restore whatever damage has occurred. The determining factors for that radiation injury are the dose, how much was I exposed to, my total dose, and then the rate. Was it I worked in an environment that every single day I was exposed to a small amount for many, many years? I worked there for 20 years and I got this little bit of radiation exposure every day. Or was it Chernobyl where an atomic bomb was dropped, and I got a ton of radiation in 5 minutes? So those are the determining factors for radiation injury. Short-term effects are seen within minutes or days or even weeks. This is the large amount in a short time, and it can lead to what's called acute radiation syndrome. Those are going to be your quick onset symptoms like nausea, vomiting, diarrhea, hair loss, redness, hemorrhage. This typically is not applicable in dentistry. We don't use that much radiation. The long-term effects of radiation are those effects that appear over years, months, decades, and even sometimes generations. This is where you've been exposed to a small amount of radiation over a long period of time, and it has been linked to cancer, birth abnormalities, and genetic defects. So those you can see are more long-term effects. There are certain cells in our body that are more sensitive to radiation. And if you just think about when you go to have an x-ray or when we do an x-ray on a patient, the body parts that we cover, the cells that are most radiosensitive are blood cells. So the small lymphocyte is the most sensitive cell in our body, but any blood cells, bone marrow, reproductive cells, anything that is rapidly dividing, cells that are immature, like children, are more sensitive to radiation because a lot of their cells are just starting. They haven't been differentiated into their specific jobs yet. If they're undifferentiated and they're rapidly dividing and they're immature, they are going to be more radiosensitive. And then cells that have a high turnover rate are also more sensitive. So I've kind of listed some on the chart for you, or on this review for you, of the ones that have the highest sensitivity down. The ones that are asked about the most, I think, are the blood cells and reproductive cells. And if you think about it, that's the first thing we cover is reproductive organs. Breast tissue on little girls is really important. Obviously, gonads, sex organs, all that has to be covered because those are very radiosensitive. Now, the radio-resistant cells are going to be more resistant to radiation exposure. They're slowly dividing, they're more specialized, and cells that have a low turnover rate. So muscle tissue, nerve tissue, mature bone and cartilage. Actually, our salivary glands, thyroid glands, both of those fall in the lower, and kidney and liver. The salivary gland and the thyroid gland do fall under, I think the salivary glands do too, but the thyroid gland for sure fall under a critical organ. Our eyes do too, because those are organs that if they're damaged, they can diminish the patient's quality of life. So critical organ doesn't necessarily mean it's the highest sensitivity to radiation. It just means that if that organ is damaged, it's definitely going to affect a patient's life. And that's why thyroid collars are so important. A thyroid isn't highly sensitive, but if your thyroid is affected, it definitely affects your body and your metabolism and the patient's life. The next thing that's discussed is radiation measurements. So we talk about the traditional versus the system international units that are used today. So exposure is the amount, the way the radiation ionizes in air is exposure. And a traditional unit was the Rinkin. And then the SI unit, or the System International unit, is now coulombs per kilogram. Those aren't exactly equal, but that's the closest comparison to the Rinkin, is that coulombs per kilogram. That's what you're going to see things in today. But that's exposure in air. Dose is the amount of energy that is absorbed by tissue. And the traditional unit was the rad. And remember, I told you these were all A's, absorbed by tissue. Traditional unit was rad, which has an A. SI unit is gray, which has an A. So I always remembered the dose being absorbed dose, and all of the A's go along with that. So 1 gray is equal to 100 rad. And then the dose equivalent is the next measurement that they discuss. And the equivalent is basically telling us the biologic effects, which is an E. Equivalent is an E. The biologic effects on tissues. How is that really going to affect my tissue? You know, what kind of damage are we talking here? So that is equivalent. The traditional unit for that was the Rinkin equivalent in man, which was the RIM. The SI unit is the sievert. And just like 1 gray is 100 rad, 1 sievert is 100 rem. Typically, when they do our little badges and we send those in to be checked to see how much exposure we're receiving at our place of work, it's usually in millirem or millisieverts. Everything is usually in milli because it's so little that they have to express it in a much smaller measurement than the rem. All right. Sources of radiation exposure. Background radiation makes up about we get about 3.1 millisieverts of background radiation that is natural in a year. And we get about 3.1 millisieverts per year of medical. Medical makes up the biggest, obviously, because we all have x-rays. You know, if you're sick, they may do a chest x-ray. If you break something, they're going to do an x-ray. In dentistry, you get your x-rays. So all of those make up our human-made sources of radiation. But the background radiation is naturally occurring, found in the earth or from the sun or space. And that can be affected by where a person lives as well. If you live at a higher elevation or altitude, like Colorado, they are exposed to a little bit more. The type of home you live in can even affect that. A brick home has more naturally occurring radiation than a wood home. So all of those things are kind of interesting. That's just kind of for your information. The only thing you'd really want to remember is that medical radiation, which includes us, contributes 3.1, but background radiation contributes an equal amount. So patient exposure and dose. I put a Lara next to this. The things we want to remember as a dental radiographer is we want to keep it as low as possible. We don't want to expose them to unnecessary x-rays for our own gain. Like if we just want to impress our doctor or we want a better grade on something, we don't just keep taking x-rays until we get that perfect image. We want to always put our patient first and think about that. So receptor choice. We have digital receptors in our clinic, and we're going to use those because those reduce exposure by 50 to 90%. If you were using film, F-speed should be the only type of film being used. It decreases our exposure from D-speed by 60%. So there's a huge reduction there. Digital sensors, the one thing with digital, I don't know why I'm wanting to call it receptor, but a digital sensor is when a unit is preset for these sensors, it is very important that they are set to only the exposure factors that a sensor requires. what we saw happening were many dentists, when they made that conversion from film to digital, left their exposure factors the same, because in digital, you have the ability to window level up and down and change that brightness or that density with your mouse. So as long as that sensor received enough radiation, you could always window it down, but you can't give it more radiation than what it got. So a lot of dentists would leave their exposure factors high, which kind of defeats the whole purpose if you're concerned about radiation exposure to your patients. So you always want to make sure that that's been set correctly. We also want to make sure that we're using collimation. Collimation for us is using our beam alignment devices, which is our XCP. If we're using something to line that image up correctly with the little aiming ring, there's far less chance of us needing a retake. If we're just trying to eyeball it, we're human, we make mistakes, and there's a much better chance that you're going to either have overlap, or you're going to have foreshortening, elongation, or you might miss completely what you're trying to achieve. So beam alignment devices are very important. When we're asking questions about patient exposure and dose and ALARA, the very best scenario would be to use a rectangular 16-inch PID with digital. The reality of it is we use the round, which is 2.75 inches across. The rectangle is just slightly larger than your sensor. We do that due to operator error. The little rectangular one is much more difficult to line it up with and to remember to change it in the right direction every time. So they were seeing, especially with students, dental students and hygiene students, that there were many retakes because of the mispositioning of that rectangular collimator. So we went to the round, which is the next best thing. But if you're asked on a question, the very lowest dose to your patient is going to be a 16-inch rectangular collimator with a digital sensor. For technique, we want to make sure if we are able to increase that target to receptor distance by using a 16-inch PID and using that paralleling technique when possible, which is using that XCP. So risk versus benefit of dental images, where this comes in is prescribing of x-rays. Like I said, the doctor has it rests on the doctor to prescribe x-rays. Reality of it is, as dental hygienists, when we're out there, our doctors kind of give us the knowledge and calibration as to when they would like x-rays and when they won't do x-rays. And it is up to us to follow that or to consult with them if we're in any doubt. We always want to think about risk versus benefit. So let's say you had a pregnant patient. I'm not going to take x-rays unless I really feel like she's going to benefit from them. If she comes in with active infection and pain, I'm going to lead apron her probably twice just to make her feel better. And I'm going to go ahead and get an x-ray, and I'm going to practice ALARA in every possible way I can. But if she's not having any problem, I'm not going to expose her to x-rays. And we talked about the patient that has no decay, that's 40 years old and has really great home care. I'm probably not going to expose them every year either, because I don't want to unnecessarily expose someone to radiation when the benefit doesn't outweigh the risk. So for those kinds of patients, I don't feel it's necessary. Doctors usually don't feel it's necessary, and they usually make some sort of agreement with the dentist as to how long to wait for their x-rays. Okay, that's basically chapter 4 in a nutshell. Chapter 5 is just radiation protection, and it's they're basically just some of the stuff we've already talked about. With patient protection, there are things we can do before, during, and after the exposure of our patient to be sure that we're protecting them. We only want to prescribe necessary images. The doctor's going to prescribe them. Remember, that's always the answer. The doctor prescribes. We're going to use properly approved equipment. We don't want to be working with a cone-shaped PID. We don't want to be using a unit that is misfiring or is leaking oil or any of those things. We want to make sure we have accepted filtration, collimation, and the proper PID length. That's all the things we can check out before we expose a patient. Then during the patient exposure, we're going to use the thyroid collar if it's an intraoral exam. For all X-ray exams, we can use the lead apron, but only for intraoral for the thyroid collar. We're going to use digital sensors if they're available to us. And if we must use film, we're going to use an F speed only. We're going to use our XCP. We're going to make sure we have proper exposure selections, meaning KVP, time, anything that we have the ability to adjust and make sure it's correct. In our units, that would be referring to making sure that in the room that's closest to your locker room, on that one, you have to make sure you select the little computer. There's a piece of film and a computer, and you want to make sure that it's on digital, which means you want that little light to light up by the computer. And then we always want to make sure that we're selecting adult or child. Child drops it almost by half. So we want to make sure we're not using an adult exposure on a kiddo. And we want to avoid retakes whenever possible. Make sure that you have things lined up correctly. Make sure that your XCP ring, that you're sighting through, and that you're definitely going to be reaching the entire sensor and not cone cutting. You want to make sure that you have your sensor placed correctly so that you don't have the corded side towards radiation, which is going to require a retake to your patient. Then for after exposure, you just want to make sure that if it was film, that you're very careful in how you handle that. You don't expose it, that everything is done correctly, and proper processing and image retrieval of digital images is also important. For operator protection, which is you, we want to follow protection guidelines. We must avoid the primary beam. Distance, we want to be 6 feet from the source of radiation. If that 6 foot distance is not possible, then a protective barrier must be used. You must stand behind a wall that's either lead lined or is the building materials have been constructed thick enough that they protect you. Then we want to position ourselves perpendicular to that primary beam at a 90 to 135 degree angle up to the beam. You never hold an IR for a patient, and you never ever hold or stabilize the X-ray tube. Shielding, if that's necessary, it needs to be a barrier that protects the operator from the primary beam as well as potential scatter radiation. Some of those shielding barriers could be the wall. Like I said, it needs to be a specific thickness. Leaded glass windows. If you look at our radiation, our radiography rooms, they have the little silver kind of crisscross hatches. That's lead in that window. Because in a pano, if your patient moves a lot, you might as well take your finger off the exposure button and stop right there because it's probably going to ruin the image. So that's why it's important to be watching. Radiation monitoring is just the monitoring of your equipment, which should be evaluated regularly for leakage radiation. The radiation monitoring badges that you wear, those badges, like I said, will absorb any radiation that you may be receiving while you're working in that environment. And those little badges are sent in a specific time interval. And then it's cumulative. So they keep a running history. No matter if you change jobs or whatever, wherever you work, there's a running history of how much radiation exposure you've had. These little badges need to be stored in a radiation safe zone. So you wouldn't want to store them in a room where x-rays are being taken. You don't want to store them in the sun or in the heat because that can affect them. And remember that they should always be worn at the waist level, unless, of course, like when I worked in as a red tech, I would wear the skirt and the vest. So we had to wear ours kind of out on the collar where they were exposed, because if you put them under lead, they're not going to absorb anything. The maximum permissible dose is the dose equivalent that a body is permitted to receive in a specific period with little to no injury. So for an occupational worker, someone like us that works around radiation, 50 millisieverts per year is the maximum permissible dose. If I were a pregnant dental personnel or occupational person, 0.5 millisieverts per month during your pregnancy. This is the question that you were not given a correct answer on the test. This is the one that I gave you guys all the point for. So it should have been 0.5 millisieverts per month while you're pregnant. Then the maximum permissible dose for a non-occupational person is only 1 millisievert per year. And then if we wanted to add up our cumulative occupational dose, we are going to take the worker's age, multiply it by 10. So I'm 52. So if I multiply that by 10, my cumulative occupational dose at this point of my life should not exceed 520 millisieverts. We always practice ALARA. And what does ALARA mean? As low as reasonably achievable. So that is basically all that gets us up to where we were at the end of chapter 5. I have, if you guys go to your modules and scroll all the way to the bottom, the very last module says radiography videos. If you click on the first one that says X-ray tube and components, you'll see that it comes up and it says youtube.com refused to connect. Is that what yours says? Is anybody doing this with me?
Yeah,
That's what mine says.
Okay, so if you see up at the top where it says X-ray tube and components, and then there's a little tiny arrow next to it, if you click on that arrow, it'll take you to the site. And if you go to history, it should all be there. Can you guys see those? If you scroll through.
Yeah, is it the Clover learning?
Is it what now?
The Clover learning?
Yes. Okay, so there's a bunch of different ones. There's the inverse square law word problem, Compton scattering. Let's see, those. I'm going to get rid of a couple of these. Let's see, we've got Compton scattering in here twice. There's one with the X-ray beam and photon wavelengths. How does an X-ray work? Inverse square law problem. I'm getting rid of that other one. Inverse square law explained. Understanding KVP and mass, and then the X-ray tube and components. Can you guys see all of those on there?
I have 4 that I can see in total.
Have you gone to history?
Give me 1 second.
Over to the left.
Okay, I gotcha.
Okay, so go through those. That's going to be part of your assignment. Like I said, they're not super long. just like maybe one of them's 3 minutes, one of them's 7 minutes, 6 minutes, 2 minutes. So they're not real long, but I think especially since you've heard this fresh now, if you watch those, I think that'll give you that visual so that it'll help maybe solidify the material in your mind. So it'll be easier for it to stick. And basically that's all I have for you guys today. What I was going to do is I am going to you guys were interested in knowing about the quiz. Would you guys like me to read through it? Or do you still have an interest in hearing like the questions and what we missed?
I would like to.
Is everybody okay with that? I'm going to go through. I would ask that you not record